Hi and welcome back to another series of clips here. We are looking this time at rate equations, specifically kinetics, year 2 chemistry this time. In the previous set of kinetics videos we looked at year 1 AS chemistry, specifically looking at the Maxwell-Boltzmann distribution and how we could affect that distribution and its subsequent effect on the rate, knowing that we have an appreciation now that the rate of an experiment is largely proportional to various factors, one of which is concentration. And we know that it is possible to have a measurable rate whereby if we know the concentration, we can deem the effect or see what the effect of the concentration is by doing a series of experiments. When we derive a rate equation, we can establish that the concentration is proportional to the rate via a powered function. So the concentration of A will have numerically a power. We're going to call that X in this example. And if we were to have a reaction whereby A plus B, let's say plus C as well, could combine to make D, so a very theoretical experiment here, but we've got 3 reagents. It's possible, therefore, that the rate equation could be equal to a product of all of those 3 concentrations, A, B and C, each to their power of X, Y and Z. As I say, X, Y and Z are what are known as the order of reaction, and each power is the order of reaction with respect to the concentration that you're looking at. X, the order of reaction with respect to A, Y, the order of reaction with respect to B, and so on. This will give us this rate equation. The rate equation would be, as we say, the product of all those terms multiplied by a value called the rate constant. And we'll come back to that in a later clip. We would do a series of experiments and we would derive experimentally through practicals what the effect on changing the concentration would be upon the rate. Typically, X, Y or Z would equal 0, 1 or 2 for the purposes available. Each of these values tells you a different thing. So we would have a 0 order reaction, we could have a first order reaction, and we could obviously have a second order reaction with respect to each of the concentrations, depending on which the substance was. If we use 0 first and second to look at each of those concentrations in turn, if we establish that A was 0 order with respect to its concentration, it wouldn't matter what we do to the concentration. So if we said the concentration was 0.1 and we doubled that concentration to 0.2, let's say moles per litre, then the concentration 0.1 to the 0 mathematically equals 1. Likewise, 0.2 to the 0 also equals 1, showing us that no matter what the concentration is, there is no effect on the numerical rate value. Saying that, 0 order reactions would be independent of the concentration. Changing the concentration has no effect on the rate, and we would say that the rate is 0 order with respect to A. If we were to write the rate equation, we may see the absence of that A term, and when we write the final equation based on what we'll discuss here, I'll illustrate that further. Likewise, if we were to look then at the concentration of B, and we say, for example, that it is first order, if we take these 2 values and we say that the concentration this time was 3 to the 1, that is going to give us a value of 3. If we were to perhaps double that concentration from 3 and this time go to 6, 6 to the 1 numerically is 6, and what we can see is the doubling of the concentration from 3 to 6 has subsequently led to a doubling of that rate in there, which means that we can say that first order reactions are therefore directly proportional to each other. If you double the concentration of this reagent, the rate will double. Likewise, if you were to triple the concentration, the rate would also triple. And we would see that designated by the 1 power next to the concentration. Likewise, with zeros, where the entire term disappears, you may often not see that number 1, therefore we have to assume it's there. Moving to the final one, if we complete the set and say that C is second order with respect to its concentration, if we again take a concentration, let's say of 2 moles per litre, and we double that concentration to 4, 2 to the 2 squared, is equal to 4, whereas 4 squared is equal to 16. Here we've doubled the concentration from 2 to 4, but what we're seeing here is a multiplication by 4 for the rate. This is said to be a second order. If we double the concentration of a second order reaction, the rate will go up by 4, 2 squared. Likewise, if we were to triple it, for a first order, it will go up by 3, but a tripled concentration for a second order reaction will go up by 9, 3 squared. That means then that we can now establish a true rate equation based on what we've just discussed, and we would then be able to rewrite the original rate equations with our x, y's and z's which were unknown. We would write the rate equation being k multiplied by a to the 0 would be 1, which means any number multiplied by 1 doesn't change, and therefore for the purposes of the rate equation we can ignore 0 order concentrations and omit them from the rate equation. We wouldn't need to write the number 1 above the B concentration because numerically we can assume that it's there. We would write the 2 though for the C to make sure we know that this is second order with respect to C. Question may also ask you for this. So in each of these individual cases, we've looked at the individual orders of reaction in our equation x, y and z there. A question may also ask you what the overall order is. And in those cases, we simply add up the individual orders with respect to each of the substances. So for C, it's 2. For B, remember, it would be 1. For A, it is 0. And therefore, the overall order for this generic made-up experiment will be third order overall. Notice in this experiment here, the rate order with respect to C was second order. This second order reaction has not come from the initial experiment. The stoichiometry of the equation, i.e. the balancing numbers in an equation, give no rise to the rate equation. You use them in equilibrium constants, whereby they become the powers of your products and reactants, half of your equilibrium constant calculation. But for rates, that same process isn't true. The balancing numbers in a chemical equation give no evidence towards the rate equation numbers. Rate equations can only be determined experimentally. And what we'll do in the next clip is we will look at some experimental data and use what we've just discussed briefly to evaluate a rate equation from some real experimental data. So I shall see you in the next one.